Okay, so today we're gonna going through puberty. Today we are going to look at some functions dealing with exponential and logarithms that we haven't quite seen before, and we're going to use our properties right now that we kind of have a good feel about all of our different properties for exponentials and logarithms, and we're going to solve. So the first ones that we've already kind of seen involve the one-to-one property. Okay, so that's when we have either an exponential function on both sides or a logarithm on both sides, and they have the same base. Or we can make them have the same base. Okay, so I don't want to spend too much time on this since we've seen it already. But if we have something like 2x equals 32, right? So we remember we can change our bases so that they're the same. So we can change 32 to 2 to the 5th, and then from this, we just look at the exponents, and we know that x is equal to 5. Okay. Similarly, for any of our logarithmic equations, okay, even though they may not look straightforward, okay, if we go through the process of isolating our variables, we may see that, okay, we do have a one-to-one property, right? So here, if I wanted to solve this, my first step would be to get rid of this minus ln3. Right? So I would add that to both sides. Well, and then I have a logarithm with the same base on both sides, so I can just use the one-to-one property to have x equals 3. Right? And the same holds true as if this was a formula. Right? If I had something like if I had something like ln of x squared minus 1 equals ln of 3, again, we would just look at the inside. I would add 1. And I would get x equals positive or minus 2. All right, so again, we've seen all of those before. But sometimes we won't have that. We won't have an exponent on both sides, or we won't have a logarithm on both sides. We might see something like this. Okay, or that. Or even, I mean, it kind of goes along with that, but something like this. All right, so today and for the rest of next week, probably, we'll see how it goes. We're going to go over a bunch of different examples dealing with this. All right, so actually, let's take a look at some of these. So the one property that we want to remember, okay, that we went over, okay, is to remember that logarithms and exponentials are inverse operations, okay? It's the same as 2x equals 4. What do you want to do? To get the x alone, we divide by 2. We do the inverse operation. If I want to get rid of an x if I want to get rid of a base that has x as its exponential, the opposite of doing that is taking the logarithm. All right. So actually, let's take a look at that log base 3 one first. All right, so if I have something with log base 3 of x equals 4, this may seem kind of out there because we haven't seen something like this before. But what we're going to do here, we're going to do something that's called exponentiate. Exponentiate makes what we have as our equation already the exponents. And what we do is we pick the base. Okay? Now, what base do we pick? Well, that depends on what logarithm we're dealing with. So here we're dealing with a log base 3. So, there we go. What we do is these become the exponents, and we're going to put a big old 3 underneath them. Now, if you don't have the room to do that, right, you would just rewrite it 3 log base 3 of x equals 3 to the 4th. Okay, whatever your old equation was, right, that's going to be on either side as your exponents. Okay, and we know that this has to be true because this is true. Right? I could have picked any base and this would still be true. Right? I could have picked e. I could make this e log base 3 of x equals e to the 4th. It wouldn't help me solve anything, but it would be true because of our one-to-one property. Right? So we choose whatever base that will get rid of this log base 3. So our property tells us that these two eliminate each other. So the only thing you're left with on the left side is x. And on the right side, well, 3 to the 4th, that's just a number, right? 3 times 3 times 3 times 3. So we get x equals 81. All right, so that's one way of doing it. The other way you could have done it, I'll do it in parentheses, is you could have, in this case, you can't always do this, but if it looks like this, you can always switch it to an exponential, right? So remember, before we had, log base a of y equals x, we could change that to x to the a equals y, right? So this would become 3 to the 4th equals x. And again, we get x equals 81. Okay, so there's a few ways to do it if we have a logarithm. If we have an exponent, let's check that one out. All right, now I have e to the x equals 7. That's a gross easy. Okay, so e is a weird number, right? It's an irrational number. 7's a prime number, so there's no way I can get them to have the same base. I can't change it. So we can't use the one-to-one property. So in order to move the x down, okay, we have to remember our logarithmic properties, right? If I have a logarithm and an exponent, I can move the exponent down to the front. So again, I could pick any logarithm to move that. I could pick log base 10, right? But then I would have to calculate log of 7. It's a weird number. I want to stay away from decimals, infinite decimals. So the opposite of base e, okay, remember log base e is our natural log. So I would take the natural log of both sides. In doing that, the natural log and the exponential cancel out, right? And the reason that this x can be written by itself is because we bring it to the front, and I can just have x. So x is equal to the natural log of 7. Now again, I may have mentioned this. Unless they tell you round to the 10th or round to the 100th or whatever, leave your answer like this. This is more exact, okay? No decimals, no rounding. But if they asked you to do it, right, you would just hit the ln button here, type in 7, and there I would say 1.946. Okay. Usually rounding to the thousandths place is pretty accurate. So if I'm asking you, I'll usually say 3 decimal places, right? So 1.94, and then we'll round that up to a 6. All right. Let's take a look at one more before we get into some harder stuff. Okay, so here I have log x equals -1. Now again, this one is our common logarithm. So if we don't see a base, it's base 10. Right? So since that's our base, and I'm dealing with a logarithm, we're going to do our exponentiate. So for both of these, I'm going to have a base 10. Then up here, I'm going to have log of x. And here, I'm going to have -1. The 10 to the log cancel each other out. You're left with x. Now just be careful here. Remember, a negative exponent gives us a fraction. Okay, so for that one, we get 1/10, or 1/10, 0.1. Any questions so far? All right, let's take a look at a more challenging one. Okay, so we've got a few things going on here. 3 times 2 to the x equals 42. Okay, so outside of the, well, including the logarithm and the exponents, okay, we handle these, we approach these algebraically like we always do. Okay, so we work from the outside in order to isolate the x, right? We're going to perform all of our opposite operations. But here we have this extra part, right? This 3 on the outside. So I can't do the logarithm right away because this 3 is stopping me, right? Like if I had something like 3 times x minus 1 equals 12. Well, I mean, you could distribute the 3 and then start to solve. But one good step, you know, you could divide by the 3. I can't add 1 until I get rid of that 3. Right? So it's the same process. Except here, right, there's no way I can distribute. I cannot enforce this enough, okay? This is not equal to 6 to the x. You cannot multiply those two because this x is stopping you. All right? Your order of operations does not allow that to happen. Okay, if I see that, I'll send you an angry email. Do not multiply those two. What we have to do is divide by 3 to get rid of it. Okay, so you may have to perform other operations before or after you do the logarithm or exponential part. All right, so just be aware of that. So dividing by 3, I'm left with 2 to the x on the right side, on the left side. Okay, and then on the left side, right side, I get my directions mixed up today. I get 14. Right, so I have 2 to the x equals 14. So the next thing you say to yourself is, can this be 1 to 1? Well, 2 to the x, that's already a prime number. I can't break that down. 14, there's no way I can make that an exponent, right? It's 2 times 7. So I want to get rid of this base of 2. So I'm going to choose log base 2. I'm going to put it on both sides. Inside the parentheses, go what's on other side, what's on each side. Okay. So normally I would just write log 2, but I don't have enough room here, so I just do it as an extra step. Okay, so now I've taken the log base 2 of both sides. On my left side, well, that's an inverse operation. I'm just left with x. On the right side, that's a number. Log base 2 of 14 is just a value. Again, if you're not asked to round or anything, leave it like this. Okay, I know what this means. I know it's the right answer. If they say rounded to 3 decimal places, again, there's unless you have a fancy calculator, if you're using an online application, you could type this in. But if you have a basic calculator, there's no log base 2, right? So for your final answer, or in the process of finding your final answer, you may have to do the change of base, which is what we did yesterday, or I'm sorry, Wednesday, right? So I like to use the natural log. You can use any log-based part that you would like. Right, so that would become the natural log of 14 over the natural log of 2. Remember, it's the large number goes in the numerator and your base goes in the denominator. Now that I can calculate. Okay, the natural log of 14. Again, please make sure to close your parentheses afterwards. Divided by the natural log of 2. So there, I would say the answer is approximately 3.807. Right? And anytime I calculate something like this, and it's not an exact answer, I use these squiggly equal marks, which means approximately. Right? And that just shows you that either I rounded or I estimated, but most of the time it means that I rounded. And that's what we have there. All right, yeah, we got time. Let's do one more. All right, so here we have another algebraic one where we might have to take some steps before we do anything. Is that the one I want to do? Yeah, I'll save that for next week. All right. So again, we work from the outside in to isolate the x. All right, so I can't take the natural log because I have this minus 7 here. Well, how do we get rid of a minus 7? We add 7. Okay, so in adding 7 to both sides, our result is e to the x equals 30. So now that that's alone, okay, I can do the opposite of e, which is the natural log. Oops, I forgot my parentheses. And the natural log of 30, again, that's fine as its own answer, but let's just see what it's equal to. .401, we'll say. All right. Any questions about solving?